So this is, as you can see, this is a second class. And I said I changed. It's not that I'm that absent-minded. It's just that I changed the order because I felt that it's better for others to do my work. Yes. So the more you know about persistent homology and stuff, the easier the job for me. So that's one thing. The second thing is that I have to confess, and so my policy is to be sincere with my students. A, because I feel better morally, so it's easier for me to sleep. And B, I have this naive belief that people will actually appreciate the fact that I'm sincere. In practice, it doesn't work like that. They never believe me when I'm telling the plain truth, because truth can be so simple and obvious. On the other hand, they believe any outrageous confabulation that I'll sell them, yes, for some reason. But these are my undergraduate students, so I hope my policy pays off. And also, so why did I make that introduction? Because I have to confess I prepared too much. So yesterday was what? I will never finish it. And I talked a bit with Fred. And so I'll make some changes. I made some changes. Also, I feel like a cat up with the tree. So I prepared. So now I have to get down, yes, to the basics. But, you know, cats don't like getting down off trees. On the other hand, have you seen many cat skeletons up trees? No. So they make a lot of noise, so they survive. So I hope I'll survive as well, okay? That's what I'm trying to say. So having said all that, let's start. So, of course, you see there is the couple of words which you like so much, persistent homology. There is Forman Ricci curvature. What can I say? I mean, after all, you couldn't expect to get rid of it so fast. And there is this new thing. So before talking about discrete Morse theory, I thought, we talked with Roberto as well, that it might be nice to talk about the classical Morse theory. This is Marston Morse. So Morse theory gives you a way to decompose a manifold into basic blocks, which you call handles. And each handle is homeomorphic to a D ball and contains what is called a critical point. So how does that work? And to each critical point, we attach a number. That's good, because in mathematics, it's good to have a mensuration. You would like to attach numbers to something: volumes, lengths, energy, indices, and this we attach here. So I didn't work enough on the slide here, but this is the image. It's taken from a paper of Banchoff. I was lazy. I have another drawing of mine, but I couldn't find. I mean, I could have found it. So the idea is to look at a torus which stands like that on a plane. So you have a height function. Some people call it h. Here is called f. So the height function says at what height you are on your torus, yes? So the point P sits on the plane, and the way you go up, this is a height function here. So we have 4 special points over the plane V, or plane pi, or whatever the name you prefer. And this is a drawing. I hope nobody will get angry. Von Harcher's book, I think. So there is the torus, so we have the level sets. Also, I should say, when you see all this stuff, level sets, what pops in your mind should be calculus 2. Yes? I mean, people get frightened, oh, Morse theory, but it's just calculus, good old-fashioned vector calculus. Okay? At least the classical theory. Of course, but in a smart way. So we have this: if you have a height, you have level functions, or level sets, sorry. And so if you get up to this height, then you look at all the points which are lower than it, okay? So you start from here, then you have the level sets, They get kind of strange, then they divide, you are on this pair of pens, and so on and so forth. Okay, so that's what happens. I'll let you contemplate this slide, and I'll go back to the drawing. I can do my own drawing, but it's in a sense it's easier this way, okay? So time out. I forgot to ask, did you learn Morse theory? Everybody? How many? Okay, so I apologize. You guys will be bored. You'll be bored now, the other guys will be bored later, okay? So nobody gets exempted from being bored. Okay, so yeah, so you have a zero empty set here, you have 1 point here, then everything below this hole is a disk, topological disk, and so on and so forth. Then you have some cylinders and stuff like that. Yes, you have a cylinder. If you cut your torus here, you have something like this, which you can open, and it's a cylinder, of course. Topology after all. Okay, and so on and so forth. Okay, so there is a canonical way of doing this stuff, which would be to describe it in a way which using handles, or if you want to look at the homotopy type. So each move means attaching a cell. So passing from here from 1 to 2 means attaching a 0 cell. From 2 to 3, remember how it goes, means attaching a 2 cell, and so forth, a cylinder, and so on and so forth. So it's just how you are doing. Nothing here, then you are attaching a 1 cell, then you're attaching another 1 cell, and then a 2 cell on top, and you're finished. You get the torus. Okay, so formally, so okay, I'm skipping this slide for the moment. So what does it mean to attach a cell? Simply, it means you are attaching or gluing the cell, which is the ball to X, to glue it on the whole boundary. So this is the correct way of doing it. This is the wrong way of doing it. This is a glue. This is a cell attaching. This is not a cell attaching. Okay, and if you want to do it in the technical manner, so people don't understand anything, but you can write a textbook of classical textbook of topology. That's what we need to have an equivalence relation, and okay. So since at some point in time these slides will be available, I can say, okay, those who want can do it. But this is canonical way of gluing as topologies do it. Okay. So now we come to the definition, technical definition, not the intuitive one, which I use formally when talking about Morse. Sorry, about Forman's Ricci curvature. Finite CW complex is a topological space such that you can present it as a finite nested sequence where passing from xi to xi plus 1 or x to xi from x minus 1 means attaching a cell. And the trick is that you start from the empty set, you finish the whole space, and this one needs to be a 0 cell. So 0 cell, you attach 1 cell or 2 cells, whatever, cells. Okay. So this is a nice way of defining CW complexes, and it sounds very easy. So you saw our drawing before. So I have, let's say, a disk, and that I take a handle and I attach it. So one problem is that this is a decent way of doing it, but you can do it like this. You can do it with a twist. It's topology after all. Yeah. So you can glue something which is, I don't know, basically a ball, but a disk, but switching somehow the orientation of the boundaries, you attach a projective plane or something like that, or maybe strip. So it can be kind of interesting. That's what I'm trying to say. Okay. So now we are going back to Morse. So Morse did it for smooth surfaces. I said calculus 2. Okay, so think calculus 2. You really can teach this stuff well, perhaps not the gluing formally, but these things, and that's how the ideas go. You do it on smooth surfaces. So smooth surfaces are given by parametrizations. So you can talk about critical points. My critical points are these ones. Yes, sorry. Perhaps I should have been more specific. But it's clear that when you pass from here to here, nothing really changes. You get a larger disk, yes, or larger cylinder. But something happens when you pass from here to here. Suddenly you have a point. When you pass from here to here, your level set is suddenly not circle anymore, but an eight figure, a Lemni scale, then you have two separate disks and so on and so forth. So these are the problematic points. So these are the critical points, which I called, if you remember, sorry, PQRS. Okay. So these are the points. And okay, these are the critical points. So it turns out that in suitable local coordinates, calculus or classical differential geometry at most, these are critical points satisfy this condition. The df to dx equals df to dy equals 0. And that can be made a bit stronger, significantly stronger, by saying that in local coordinates that of my choice, I might choose them in such a manner that at the bottom of the torus, I'm lazy, but I'm doing this so you won't believe I can't draw a torus. Any topologist knows how to draw a torus. Yes, this is a torus. So this is P, Q, R, S. And I remember talking to a very smart guy from computer graphics. Wow, you mathematicians, you draw this torus so simple. I don't know how you do it. Smart brains. Well, I don't know. It takes, because we are not good at drawing, so we have to do our shortcuts. Anyhow, so at this point, it looks like this. At this point, it looks like this. It looks like a cap. So, and of course, this is an x squared plus y squared. And here is the same with a minus. But you are at height 1 minus something. And at these points, you have a saddle point. Yes, a classical saddle point. Okay, which I also know how to draw, by the way. This is one way of doing it. Anyhow, so that's important. Okay. So you have a number of minus signs. So you have two minus signs here. You have a minus, only one minus sign here, and you don't have minuses here. So the number of minus signs equals the dimension of the cell that you attach when you pass from level A to level B, so to say. And that's important. If you remember, I wanted to code somehow, to encode by a number what I'm doing topologically. So topology is pretty. You can make nice pictures, even nicer than this, but it's hard to compute. I mean, you want numbers. Mathematicians like numbers. Students like numbers even more. So this is a way to do it. You just look at the numbers of minus signs, which means a simple count. So we have the definition which says that if you have a smooth manifold of dimension n, then F is a smooth function with real values. A point on P is a critical point if the differential is 0. that means that precisely this condition we saw for the torus holds. And then the number is called, f of p is called a critical value. So you have critical points. To each critical point, you attach a critical value. Okay, so this is straightforward. The whole difference is between the T2, I have an MN, but otherwise it's the same. So there are two kinds of critical points. I have a degenerate points and the non-degenerate. So I'm interested in non-degenerate points. And these are, so I look not only at the first derivative, but I look at the second derivative. So again, calculus 2. First derivative, I have a gradient and I have the different ones. And it's not just one way of defining a first derivative. But in calculus, you have one way of defining the second derivative, and there's a Hessian matrix and this determinant, by the way. So 1.5 ways. There is a smarter way of defining the second derivative, and that's called curvature, by the way. But here we are just looking at the Hessian. So if this matrix is non-singular, then the point is called non-degenerate. So then you can define the index as a maximal dimension of a subspace on which H is negatively defined, if negatively definite, I don't know. So the index of H is just the index of F at that point. That makes some sense. So the first important results, I thought I made corrections, but I forgot this S. But at least I did not eat it. It shows that the behavior of F at the point P, I mean, the behavior of the height function when you pass through frequent points, which interests us, because as we said, it encodes the way I'm gluing, how I keep building my torus from simple pieces. It's determined by the index. So more precisely, we have this theorem that says that if I have a non-degenerate point of a function f, there exists a coordinate system in some neighborhood, which, I mean, I don't know. I think that one somehow assumes nowadays that having a coordinate system, it comes with a choice of the neighborhood. It doesn't matter. Such that f of x, x of I of p is 0, so you put your coordinate systems at there, and f of x is f of p minus x1 squared, minus something, plus, and then you have the pluses. So locally, you write your function in this manner. And of course, so before that, we had x1 squared plus y x2 squared. This was one expression. The other was, let's say, this one. And the other was something like that. So instead of x1, I'm writing x2, x and y, I'm writing x1 and x2. But it's the same, yes? That's what we did for the torus, and we do it here in the more general manner. And the number of minuses, we said, is the index, and for some reason, I denoted this by lambda. I think that I followed a classical textbook. You'll see immediately. Okay, so it's very simple, theoretically at least. If I find the coordinate system, then all I have to do is count the minuses. But of course, in practice, you might have some problem finding this coordinate system. It's one thing to say, I know how it's possible, and the other way to write down a recipe of doing it, actually. Okay, so, but let's say I did it, and it's very simple, yes? So in a sense, I have these very simple expressions, and all I have to do is to count minuses. The only thing is that in practice, it would be boring if you would discuss only about toruses. I never saw anyone who did this with another example, because it's nice. It has all the possible configurations. But sorry, I'm not transparent. I'm working on that, but the food is too good. So, and yes, it encodes what we want the best. The sphere would be simpler, but much more boring. Yeah. Beyond that, I don't know how to do it. But it would be really boring if everything we did was just to encode the torus and stuff like that. Yes. I mean, that would be a good thing to do something interesting in calculus 2 for a good class. But it wouldn't mean anything. So in practice, height function doesn't mean height, actual height. It might mean, but, and this is a promo. So this is my plane, this is a torus, but what happens is this is a plane and this is a torus, or this is a torus, or whatever, yes? So this is one way of doing it. The other thing is to think what a height function might be. And there are nice height functions, much more interesting. One for smooth manifolds, which are just that you look at the energy functional of paths. So if you have a smooth manifold, this is a smooth manifold for me. Okay, smooth enough, smooth enough. And I have paths in it. I can talk about the energy of the path going from here to here, for instance, to this to path pi. I write an integral, which is energy. And of course, this guy is a number. So it gives me a height in a sense that if I have a different longer path, for instance, more widening path, it might have higher energy, yes? And that's, it might seem perhaps, I don't know, if you know a bit of Morse theory, it's of course, but if you don't, perhaps it sounds strange. But it turns out that if you choose this smart way of, if you choose, what another name for choice? Okay. If you select the right smart choice, sorry, I'm stressed. So the good selection of a choice would be to pick, if you pick up your right selection of a choice for a height function, that energy function of paths, that gives you the geodesics as critical points. So instead of having, if you look at this thing and you look at its geodesics, so you look at paths on the torus, so the critical points would be precisely the geodesics, the shortest path. Okay, straightest path, I should say here. That's what Morse did and revolutionized the whole field of mathematics, and we still do that. Yeah.
But this was then the function of the path space.
Yes, of course. So once you have the right idea, so that's okay. So it's like the trick with how you put an elephant in the fridge, yeah? You first you open the door that's coming up with this idea, then you have to put the elephant inside, and then slowly, not to break the door, you close it. Yes. So choosing the way to put the elephant inside is the second part of the good mathematics. So I would say that this is smart, but this is already genius Morse. I mean, I think that's the trick. So this brings you a lot of generalizations. And I'll show you, by the way, some other strange Morse functions today, okay? And there is another, those, I already mentioned Alexandrov spaces, and now the class is smaller. So I ask again, how many of you know what Alexandrov space is? Okay, thanks. So I won't get into it. It would be nice, but it's another course. If you organize something, another mini course on discrete geometry, whatever. But I would say that these are the, I know what I want to say. I'm trying to say it nicely. It's, I can want to use two words, decent and general. So I don't know if they are the most decent general metric spaces or the most general decent metric spaces. So you have metric spaces with some kind of very vague but very powerful notion of curvature. Okay. So they're very decent. Okay, you know what? If you'll have time, I'll say something about Alexandrov spaces, okay? Sorry. But they're essential in modern mathematics. You can't do a lot of stuff without them. You can't do a lot of stuff without them. And not only in geometry, you can't do a lot of stuff of them. And what that made them a good sell. So geometers can come and try and advertise and show you nice pictures. Nobody buys that. Either you sell it as computer science or you sell it to algebraists. So the ones who made this thing important were the guys from geometric group theory, So doing small cancellations, suddenly had this super big howitzer, Berta 400 millimeters gun. And the idea of looking again as distance functions, this comes from here, I would say naturally, in Alexandrov spaces, that was Perelman. So if you remember, I mentioned Perelman's name in my first lecture. Ricci curvature, the same Perelman, yes? But he worked on this kind of generalized spaces as well. So I think I should get some remuneration from Forman and Perelman because I make a lot of, I save their stuff. I should get some percentage, I think, by now. I'm not really serious. Yes. Okay. So the idea is to find nice height functions. And what is a nice height function? So I want a nice function, and a nice function will be called, of course, a Morse function if it has no degenerate critical points. So it's much easier. Again, a Morse function would be nicer. A function would be nicer. Height function would be nicer if I wouldn't have this some bad configuration, some bad critical points. And such a function is called a Morse function. Okay, so I'm sorry. I spent a lot of time putting color and pause. Yep. Yes. Hope. Okay. Linear algebra. Okay, so now I teach linear algebra this semester for my sins, So that's my punishment. So that's a good way of selling to students why you shouldn't. I mean, no, I can't explain my students that they need to know Morse theory, but yes, linear algebra is good. Boring, but good. So I should have put a pause in here between these two slides, between these two blocks. And why? Because I want Morse function. I was nice height functions. But the question is, do I have such functions? I mean, wishful thinking is wishful thinking. If you want to make it more, then you have to prove you have such objects. And the thing is that, yes, there is a result, of course, of Morse, of course, who says that Morse functions are generic. That means that if you choose an arbitrary, they're dense, so to say, in the space of direction. So if this is your plane, this is a Morse function. But what happens if you change this direction? Basically, all directions are good, except a few bad ones. And it makes a lot of sense because, again, this is my torus. It's not a torus, but it doesn't matter. So this is a good direction, and this could be a good direction. I see a different height function for it. I might have problems if I have something which is too perpendicular, too tangential, so to say, yes. Perhaps I won't get anything, yes. We'll see it later. I'm not most clear perhaps here. I'm not perhaps, for sure. So so you could say, don't worry, you're pretty happy with that. If you just throw a stone or a coin, it will land on a good function. Okay. So you can do it a bit more formally. I'm not sure I want to do it formally. So if you have two different two values A and B, A smaller than B, with no critical values between them, so it's regular and this is regular, nothing bad between, then the spaces you obtain going up to here or up to here are the same topologically. And this is more important in practice. The trick is that there is a homeomorphism, but again, as I said, mathematics is one thing to show, oh, I have something. The other way is putting your hand on it. And the way of putting your hand on it concretely is that this homeomorphism is obtained by finding a gradient field, the gradient of f. So the trick is, again, you use calculus. You want to do topology. Your tool is calculus. So you go back to calculus each time for your next idea. So you look at the gradient. And that makes a lot of sense. Again, gradients are ubiquitous in the space of image processing, for instance. Yes, so we use gradients all the time. We just descend on them the fastest. That's why we like them so much. Okay. So this is a formal result of passing through critical values. So when you pass for critical values, critical point, critical value, you going from just below the critical value point to just above it, you do it by attaching an I cell. Attaching in a continuous manner, of course. Okay, so that's very technical. So again, I did something wrong with my pose function. So we have these basic results that any compact manifold is homotopy equivalent. It's basically, it's equivalent from an homotopy viewpoint. I don't want to get technical. With a CW complex, in a very simple, in a very canonical manner, it's equivalent. You attach I cell, precisely one I cell at each critical point of index I. So if you have 7 points of index 3, you have attach 7 free balls at each one. And now the next trick is to look at the number of points of index I. So you have points from index 0 to index n. And you have, so you go, I goes from 0 to n, so you put them in a vector. So this is a Morse vector. So that's very nice because I can encode my gluing procedure. I don't have to see anything. I just give you this vector. And then I know what I'm doing, yes? I'm starting from 0. I'm attaching so many points, balls, so many 0 balls, so many 1 balls. Okay. So it's ready-made for computer use, I would say. Yeah? Computers know how to read vectors. Okay, so then, of course, what is this good for? It depends whom you are asking, but of course, for you, you saw a lot of algebraic topology these days, yes? No? I would say yes. Persistent homology. So we heard the word homology a lot. So it would be nice to hear once more, at least we know it by now. So there is this classical result which connects Morse theory, which you remember it's just calculus, plain old calculus, calculus 2, to algebraic topology, i.e. to be more concrete, to homology theory. And I have this theorem, which is called the Morse weak Morse inequalities, which connects connects the Betty numbers with the CIs. If you remember, CIs were the number of points of index, critical points of index I. So we have this connection. The beta numbers are always smaller. Their sum, alternating sum, is the same. Therefore, instead of writing this alternating sum, which we know also it's well known to the public as the Euler characteristic, we can write it in terms of these guys here. And that's very useful because once I have this vector here, I just put plus, minus, and then I get the Euler characteristic. So I reconstitute, I have a good understanding, topological understanding of my space just for looking at the critical points, which I computed using Hessian. And there is a stronger, so this is called the weak Morse inequalities, and I have some stronger ones which show this one. There is a way of doing it in this manner, going from I, not from the end, yes? So this is a strong Morse inequalities. I won't prove any of this, and I think I'm almost finished my classical Morse theory, yes. And I should say that, of course, this is not a course. I found another fun. It was not intentional. Of course, it's not a course. But if anyone wants to really learn more theory, I can only recommend Milner's book. So this is our second genius for today. This is called Morse Theory. It's easy to remember the title. And I've solved this written. Many people consider it that it's the best ever mathematical book written. It's really nice. I mean, all I told you here, it's in some 20 pages and then something like that. And then it really goes into geodesics and nice stuff. So as I said, this is, I use this expression of adusum delphini. So it's for beginners who want to get a taste of it, and then you really have to buy the whole thing. Okay, so that's what I said about classical Morse theory. So that I hope I got down from that tree. Okay. Yeah. So, as I said, Morse functions are generic. So if you choose a function, it would be a very unfortunate thing if you get not a good one. Even if you get a bad one, not a Morse function, but you jiggle it a bit by epsilon, it will be a good one. No, but you might have critical points of different indices. But in the end, the sum, yes.
That's the same composition of the same thing.
So again, take the torus. So if I choose this height function, it looks like this. But if I choose this height function, it will look the same. Oh, but also this way, yes. There might be a bad height function when I, okay. I'm sorry. It will be clearer when we get out of this smooth context. This is very nice. You have second order derivatives. You have but it's harder to imagine. We'll see that discrete topology and geometry are much easier to grasp, okay? But that's not everything today. Okay. So, so I understand your question. Thanks for pointing it out. I'm as I said, I'm trying to do a lot in a short time. And I keep forgetting some things, but since we will have a discussion section, theoretical one at least. Yeah? Yeah? What? This is a good question. Yes. Okay. So this is my good question, problem. So you see, if I want to do something in practice, and practice means discrete, I mean, for instance, complex networks or polyhedral manifolds, whatever we saw here, and any practical application, you can't use Morse theory as such. Why? Because Morse theory is defined in terms of the Hessian and the gradient. So yes, there are discrete gradient versions, but Hessian is famously or it's infamous for not lending itself to discretization because it's not an intrinsic quality. It depends on the orientation. That's the problem that you said before. Basically, that's the one. I don't have, it depends on the normal, so to say, to the surface, the Hessian, the direction. Therefore, it's problematic to discretize it. So it's famous for that. So that's why you use, for instance, Laplacians in graphs a lot, but you never, or almost never use Hessians because they don't really exist. And guess who came up with a solution? And I hear the sounds in my bank, money getting in my bank from Forman, yes. So no, it turns out that Robin Forman came out with a solution to this problem, and he introduced a discrete, let's call it combinatorial Morse theory. And I should say the following thing. He wrote not just one paper, but rather a number of papers on that. And they are very well known. As opposed to his last paper, the one of the Forman curvature, which is far less popular. But this work is very, very popular. And how much time do I have? 15 minutes? 5 minutes? Okay. So I'll just try to show you that how popular it is. Okay, and then perhaps we'll come back to it later. So how do I do something like this? Escape. Escape. Okay. So for. Oops. Oops. Okay. No. Okay. No. Okay. Control full. Sorry. How do I do full screen? How do I do full screen? Hey guys. Control L. Oh.
Maybe if you go to menu and then view or something, in the top left there's a menu thing.
No, it didn't work.
Then view is like at the top.
View full screen. Okay. When I'm facing my own computer, I'm smarter. But it's stressful. So I just want to show it, and this is based on, since then I'm sure people use it a lot more, but Forman's Morse theory was applied in many, many fields, and my name doesn't appear anywhere, so you can be convinced that it's true. So no, anyhow, I don't know. Now this one doesn't want to disappear. So it was used in visualization. Oh, so again, if you remember, to do Morse theory, I need a gradient. Talk about gradients, gradient fields. So the trick is, Forman's is also to build a discrete vector field, which is also useful per se. So that's what he did. So here he used a discrete vector fields to visualize things on a Klein bottle. Here is for imaging to decompose a bone for medical imaging in what is called quad patch. So you see basic regions, and the cost function, the height functions, if you prefer, is it's mean curvature. So, which is basically the Hessian. So to say another way of saying Hessian. How do I make this one too? Oh yes. I don't know. It doesn't. Did I do something wrong? Sorry.
Oh, no, I am not an expert on.
I'm clumsy today. And not just today, but don't tell that too loud. Ah, okay.
So this way we don't see this, for example. No, that's not that important, maybe. Or yeah.
No, it's okay. Thank you so much. Thank you. So sorry.
Take it, then you move it down.
Ah, okay. But I don't know why it appeared. Yeah. So that's one way, one application. The other, now it doesn't work. Now what? Okay. Now it doesn't work with this one. Okay. So then you can use this for mesh compression. The same guys. You can decompose using a tree structure. Again, using vector fields. And then you can track features in image sequence. So the features you want to track. So when you have a person in a city machine or something and you want to follow the important points, you paint them as critical points and you follow them. Whatever, I don't know. This is to remove topological artifacts, because so these are blood vessels, let's say, I don't know, in the lung or in the brain, whatever. And some of these red things are not real ones, are noise. They have more warps that you impose, and you want to remove them. So you look at the bad points at critical points, at the red and the noise at critical points, and you denoise them, remove them. So you use persistent in discrete Morse theory. I've heard the name before here. Yes, persistence. And you can compute Betty numbers, again doing persistent stuff. And this, you have the solidification things. You have metals, for instance. So in metals you have air bubbles and voids and inserts of impurities and stuff like that. And that's very important to understand them. And if it looks something like this, then it's clearly not good. Then it might break. Or you can think of this as some tissue with some disease in it. I don't know. It depends on your application. And even range images. Range images are images like radar or dolphins. You just see pings, yes? So they look very flat. So this is a classical range image of a forest. You see, I think as very close, medium, or very far. There is nothing in between. They look like that, yes? Like steps. So you can see a few well-known names here, like Da Silva and Gustav Carlsson, and using Morse theory of this kind of stuff. And even for networks, to do some principal component analysis, something with students and groups, and high school students love to make lives miserable to each other. So this is a way of tracking them. Okay.